Welcome to this lecture for section 1 basics and lecture 3 named types of error. So as in the previous lecture we have seen that all the measurements are prone to errors. So error is an inevitable part whenever you do the surveying. So we will in this lecture we will see types of error, and we will also look into the uh, rectification or kind of a what kind of a deal, how to deal with these types of error. So different types of error require different kind of a treatment, we will see here. So basically types of errors are classified into the three categories. First is the gross error, systematic error, third is the random error. So first we will look into the gross error. So what is gross? So what is gross error? Gross error is kind of a blunder or the carelessness of observer. So due to the carelessness of observer, the gross error occurs. Or sometimes you can also call them personal error. Take for an example, an observer is reading. Just take the same example of a reading a tape. If someone is centering and over a point this step and reading, if he does not read properly, if he does not carefully apply the tension, he does not observe temperature, or maybe when he read the temperature he does not read temperature correctly. So due to this personal, or you can say due to this observer error, or maybe we can say it is not the error, it is the individual observer's ability to read, center, and pay attention towards the detail for carrying out the work. So, due to all these limitations or the limitations in the ability of observer, or sometimes carelessness, there are some the gross error occurs. So when you change the observer, the gross error or the kind of a error also changes. So one observer, let's say, he pay very careful attention, or he is very diligent while working. So he will not produce this kind of errors or the blunders uh, compared to the other one. So when you change the observer, the gross error amount and it also changes. So now the question comes how to deal with gross errors. So we do not tolerate any gross error. We do not allow any gross errors to occur in our measurements. So to eliminate the gross error, what we can do now? This is kind of a very personal kind of a error. So generally we adopt very good field practices, good field procedure. We also say SOPs, the standard operating procedure, to perform a particular kind of a surveying operation. So we try to eliminate the gross error by adopting a good field procedure. So during the field observation, we adopt SOPs. Even during the computation and adjustment of the measurement, we also adopt good procedures and standard operating procedure, so that we can eliminate this kind of a gross error, or at least we can detect this kind of a gross error at the initial stages. So if we know that the measurement is not suitable or not within, it has some kind of a blunder, so that we can kind of rectify our measurement, or even in case we are not able to do that, in that case we will reject those measurements for our final computation and adjustment work. In that case we will have to repeat our measurement in the field, or those procedures where actually we are getting a large amount of error. So here I will try to explain you the kind of field procedures or kind of field procedure or kind of principle we observe to eliminate the gross error. So here first I will take an example of the labeling procedures. Okay. So in labeling we ensure that our label is, that labeling instrument is properly labeled. With that we also ensure that the staff is properly centered over the survey mark, and it is also labeled by checking that circular bubble. So these things we actually, before making a measurement, so we write all these steps in the SOPs, so that any, if a person changes, even a person changes, observer A and observer B, everyone will follow the same drill, so that when they take the reading, there are minimum chances of that gross errors, before fox before so that observer is also focused properly here on the staff and reading. So in labeling, we also keep one stuff here. We call it a backside, and the front we call the foresight. So there are chances that observer is reading this foresight, but actually while he is tabulating this reading, in case of into that backside. So this is a kind of a blunder. So the step procedures are kind of we define properly, so that when you take the backside reading, you need to enter it into the backside reading. So we properly create forms where they enter readings, that kind of a thing. Okay. So at the end, even if he has done some wrong during the labeling, so we also have the check, like the summation of backside minus summation of foresight should equal to the last, that RL of the last point and the minus RL of the first point that you checked might have right during the leveling. So this kind of a check we also perform if something is, some reading by mistake he has not properly entered, a backside reading he has entered into the foresight, or maybe the foresight into the backside. So by this last final checks, that kind of a checks we call them as an geometric or the independent checks. These are the independent checks formula. By this we also can detect that the particular leveling measurement is kind of subjected to the gross error, or maybe there is a blunder here. So that we actually check, and through SOPs we give them steps, and we also check in the last. This is one of the thing that how we deal to eliminate the gross error. And the second thing, we do the redundancy in measurement. What is a redundancy in a measurement? In an example, let's say from point A to B, you could have measured it only once and got a distance like 19.89 meter, but you are measuring it again twice. So when you measure a distance distance, or any, when you take a measurement to determine a physical quantity more than the number of times which is required, so the extra measurement we call them a redundant measurement. Why these are important? Because in this example, if I have only measured once, okay, and I have kept this value as my final value, I would have never known whether there was some kind of error in this measurement or not, whether it is, best possible measurement or not. So we take second time also that again measurement. So if it is 19.90 meter, we can say, oh, it is kind of the variation is acceptable. So when we do the multiple times measurement and the measurement comes around 19.89 meter, we say all those measurement are consistent. So not only we create a redundancy in measurement, we also check the consistency between them. So what do I mean to say? That I am measuring this distance more than once. If I would have measured it only once, it was sufficient. But I am reading, no, measuring the distance again. second time, third time. So that is in excess of the requirement. So that is, we call it a redundancy. Uh, After creating this redundancy, we are also checking the consistency between them. So like 19.89, 19.90 meter, they are approximately very near to each other. So we can say the measurement is consistent. Let's say if the measurement in the second or second time you performed and it comes like 18.2 meter, so this the variation is very large. Here there is a possibility of gross error. That way measurement is inconsistency. So the measurement shows inconsistency. So by this checking inconsistency, you can also check about the gross error. So if I take the example of leveling, what we do, let's say here is a level instrument and here is a staff, here is a staff back side and the forward side. So generally in a leveling activity, when we do the measurement, we take, let's suppose, first reading here, second reading here, okay, and we get the difference between level difference between the point, this point A and the point B. This measurement was sufficient because you know the difference between those 2 points. Okay, that I will call it a difference 1. But what we do, we displace this instrument a little bit and again do the measurement. We displace this instrument and again set up, level it, and then take the measurement on the same station and B, and we get the level difference 2. Okay, that is the level difference 2 between the point A and B. So this second measurement was a redundant, and the difference between the first set and the second set, let's say the difference comes 2.1 meter, and in the second set it comes 2.15. So so the difference, kind of a variation between these two, if as per your standards are within tolerance, let's say the difference is a 0.5 meter. So in the standard operating procedure, we define that whether we can accept these two measurements, we can, or I can say that I can accept only those two measurement if the difference between those, like the 2.1 and 2.15, the difference between this two reading is within some limit. Okay, if I say it should be within zero point 0.1 meter and it is coming 0.05 meter, and I am accepting it. So what I am here doing, I am trying to check the consistency between two redundant measurement. So I'll say it is okay and I'll accept it. That way I am eliminating the possibility of any gross error. So that way we also that is one of the way we do in a standard operating procedure. So we take multiple times measurement to create redundancy, and also after that redundancy we check the consistency between the different sets of readings. One of the very important, you can say, measure or the standard operating procedure that we follow to check the gross error is the independent check. What it is? So an example, if I take the example of a distance measurement, let's say a person, Ramesh, measured a distance between point A and B, and the second time you are not deploying the Ramesh, you are deploying Suresh with some other tape. You are also changing the tape, also you are also changing the observer. Suresh, now Suresh is observing the distance between A and B, and now you check whether those measurements are consistent or not. The first set done by Ramesh and the second set by Suresh, if they are consistent, so the measurement done by the Suresh we call the independent check. Here we are also changing the observer, we are also changing the instrument. That kind of a field procedure we adopt. So there, the possibility of the gross error eliminates. If I take an example of the leveling, so in the high precision leveling, in the high precision leveling, what we are doing in the high precision leveling, we, let's say that point A and the point B is there. So an observer, let's say Ramesh, is doing the leveling operation from A to B in this direction. I can say that in this direction A to B. Then for the independent check, I will deploy Suresh with a new different instrument. Observer is also different, and also at some different time. Once the Ramesh has completed, after some period, the Suresh will start the leveling from B to A, and we will check whether the difference between the A and B and the, done by Ramesh, and the difference obtained after doing the leveling from Suresh, Suresh, check whether the difference are within tolerable limit or not. So this is kind of an independent check done by the Suresh for the work done for by the Ramesh. So this way we also check if there is some kind of a gross error, the possibility is there. We check through independent measurements and eliminate those gross error. As we also earlier discussed at some point of time, one way is to check geometrically. So if I am measuring the angles of this triangle and obtaining some value, so the sum of all this triangle A, B, C should equal to 180 degree. There is no doubt in that. So if you finally measure the, if a person measure these angles and the sum of these angles are not 180 degrees, simply you can have a doubt on that measurements and you need to check it again if it is not consistent with this geometrical conditions. So I will again repeat the gross error. So gross error is just the random or the blunders done by the observers, or when the observer is not carefully doing work. So due to this the gross error comes. The example is that if you are not reading scale properly, you are not sighting where you need to sight, properly focusing. Due to this observer carelessness, the gross error occurs. And you can also say that it's a kind of a personal error, because an individual person has, or the individual observer has the ability, a limited ability to read center and pay attention compared to the other. So this way it is a very kind of a personal error also, and it varies depending on the observer. So what you do to, so how actually we deal with it. So generally we do not allow any gross error in our measurement. So to eliminate or to detect the gross error, we actually adopt good field procedures, standard operating procedure while measuring. Even while computing and adjusting, we also adopt the some good procedures and principles to eliminate or detect the gross error. So we do not allow the gross error to enter into our measurement. At the first place, we remove them. And we have also discussed some critical, principle or the points that we actually follow during our working in leveling, and the example were given by for the leveling. So these are the core principle, like you do the independent check, the geometric check, and in the geometric check we create redundancy in measurement and also check consistency. This kind of a principle you follow to eliminate the gross error. So the next error is a systematic error. So systematic error, as the name suggests, the amount of error in this kind of a systematic error is deterministic in nature, and it follows some physical law. So we will see it by an example. So let's say if you are measuring a distance between A and B, and the tape, let's say, is standardized for a temperature of at 25 degrees Celsius, and while you are measuring the temperature of the ambient was like 27 degrees Celsius. So you know that with the increase in the temperature, the tape will linearly expand. So the tape was calibrated at 25 degrees Celsius, and now you know that when the temperature rises, the tape linearly increases with the increase in temperature. And you also noted the temperature when you recorded the measurement. So now you know that what amount of error actually is being generated. So definitely you know the error, and now you can correct for this linear expansion due to this increase in the temperature, which is of the amount of 2 degrees Celsius. Now take another example of the leveling. During the leveling or the high precision leveling, we keep the instrument in the center of the between the staff. We keep this level instrument, in the middle of the staff. So uh, let's suppose there is some collimation error in the instrument. So white line is the perfect one, where the bubble tube axis and that horizontal horizon is in the same direction. But let's say is a telescope and the bubble tube has some kind of a misalignment. They are not parallel. So this condition is being shown by here by the red lines. So due to this, actually the reading should be read here, but now it is reading here. But what is happening here, actually when you read this backside, let's say this angle, the distance is same. The amount of error which is being introduced here due to this non-alignment of the both the axes, that you say E, and the distance is also same. From here to here distance are same. Okay, this both distance is same. And it is angle, so that error which are being introduced in the reading is same. So there will be no impact on the difference and the level difference between this point, let's say A, and the point B. It would remain the same even if there is some collimation error is being existed here in the instrument. So why what we are doing here? So simply the systematic here is following some physical law, okay, that the distance is there and angle will be there. Distance is same, so that angle will be made same, so the error will be the same. So this kind of a physical law is being being applied here, and we are keeping so that way the collimation error is being eliminated. So that is also example of that how we are actually dealing with this systematic error. We know the amount or the nature of the error, and we can determine it. In the first case, we can determine it that for the 2 degrees Celsius, this much of amount linear expansion will be there. So this is the error, and now we can eliminate this error. So it followed some physical law, and it also has been determined. In case of leveling, we can also determine, but we intelligently place the leveling instrument in the middle, so that way the amount of error was equal in amount, so that when you subtract the level reading here and the level reading here, that error in itself gets eliminated. So that way this also followed a physical law, and it was also deterministic. So we have countered it like by keeping the instrument in between and eliminated it during our calculations. So this was about the systematic error. So, and it's actually what is systematic error we have explained, and what and actually how to deal with it. So in case of systematic error, you know the amount of error, and it follows a kind of a physical law. And so after getting the amount of error, the direction of error, you eliminate those errors from your measurement. So the next point is the random error. What is random error? So once you have completely eliminated the gross error and you have corrected for the systematic error, the remaining one, we call it a random error. So the random error is non-deterministic in nature. You cannot determine, like the systematic error, the amount. Like in case of systematic error, you actually determine the amount of error. In random error, it is non-deterministic. You cannot determine the amount of error. And the second one is that it does not follow any physical or mathematical law. We can also say that the random errors caused due to the instrument and the human and the instrument imperfection. There's no instrument which is perfect, there's no human which is perfect. This is one of the cause for the random error. So now the question come, it does not, you cannot determine it, you cannot, it does not follow any mathematical law. So how then actually you deal with it? So we deal it. So how we deal it? So we consider the random errors as we treat them as through the probability model. We use the probability model, and we treat this random error as a random variable. Random variable. So as in the case of the systematic error, those error were following some mathematical model or some physical law. So we were dealing with them as per their relevant mathematical models or physical law. Here in case of a random error, there is no physical law that this error follow. Then we will adopt some probability model in which the random error we will call them as a random variable. So the random error will act as a random variable, and we will determine this kind of errors and their treatment as per probability models. So this random error generally occur in both the negative and the positive way, and the balance, in a balanced way it occurs. If I just draw, generally we take the normal distribution. We will discuss this topic in a very detail just for the time being. So generally we will adopt a normal distribution. So for this random errors, we normally adopt that a normal distribution. And why? Because this kind of errors occurs in both the direction. Let's say it's a zero, so some will occur in this direction, negative direction, some will occur in the positive direction. 50% of the errors will be here, 50% of error will be here. This way we adopt this model, and we will see these things in a detail in the next subsequent lectures. So the final key takeaway from this lecture is the error as of three type: gross error. We do not tolerate any kind of a gross error in our measurement. For that we adopt a good standard field procedures, standard operating procedures, and we also discuss some principles that we actually adopt to form or to formulate the standard operating procedure, like the independent checks, geometric checks, and this other different things that we discuss. That way we actually do not tolerate gross error, and actually we eliminate. And the second one is the systematic error. We eliminate it using mathematical models. Like in case of when the temperature rises, you can note the temperature and can correct the length of the or the measurement by using this increased temperature. I know. So the next is the random error. So the random error is does not follow any mathematical model. So generally we treat those errors under the probability model, and in the subsequent lectures we will actually see how we use the probability model to to kind of a deal with this random error. Thank you. We will meet in the next lecture, and after this we will start the section 2.